Good evening, boys and girls, and tonight's video is covering oscillators. This is really aimed at students currently learning about oscillators. If that's not you, possibly try one of my other videos. So what is an oscillator? Well, an oscillator is a general system or circuit that changes an output state. Here we have a signal generator which gives us an output sine wave, and we can change that frequency. We sometimes want a stable frequency for timing and flashing circuits such as these indicators here. And we're still going to be using some sort of oscillator even in an advanced timing system. We might have a flashing light like the security light, or possibly an RGB light, like these kind of hippie RGB color changing systems here. Also advanced computers such as Intel processors, or any processor as it may be, and audio-visual equipment including radio transmitters and the internet heavily rely on oscillators. So now let's have a look at some oscillator terminology. Frequency, the rate of change, how often the oscillator's output changes per second. Here we measure in hertz, kilohertz or megahertz. One cycle is indicated on a sine wave. The frequency of a waveform can be determined by first measuring the length of the cycle and then dividing 1 second by that number. For example, 10 milliseconds is 1 second divided by 10 milliseconds equals 100 Hertz. Amplitude, the total voltage of the output waveform. Here on this waveform, a peak amplitude is taken from the center point to the maximum point. Peak to peak amplitude is taken from the lowest point to the highest point. Here we can see two waves of the same frequency but at different amplitudes or voltages. The term wave shapes or waveforms refers to the actual shape of the wave created by the oscillator. Here we have a sine wave, nice and curvy, used a lot in audio. Here we have a square wave, used a lot in flashing LEDs and timing circuits in computers and digital electronics. The triangle wave, of course, is used in other timing circuits, and if we slope those to one side, we form a sawtooth wave. When we use the term stability, we are referring to how the frequency may shift slightly up or down during a small amount of time. Here we can see the frequency wobbling on this waveform, but overall its frequency is pretty stable. Frequency drift, however, is how the frequency may drift off the desired frequency over a longer period of time. This could be a result of aging components or possibly an increase in ambient temperature here. And this can be a real problem in applications such as radio. And if your radio ends up infringing elsewhere, that could be against the law. The term distortion is commonly applied anywhere we see a change in the waveform pattern that is undesired, or it could also include a change in overall amplitude that could be caused by instability in the power supply. Well, now we're finished with oscillator terminology, we can go out and get the t-shirt. Maybe you're thinking, what's the most basic form of oscillator? Well, let's have a look. Here in Proteus, I've made a simple oscillator circuit. We can see it consists of an inductor, one capacitor, a connection to ground, and I have a switch here to supply VCC. When I click the switch, VCC or voltage flows down into the inductor, and it also charges the capacitor. The inductor creates a magnetic field. The magnetic field collapses and produces back EMF or a reverse voltage, which in turn charges the capacitor. This then flows back and forth. By adding a virtual oscilloscope, we can see the oscillation taking place. Here I connect channel A to the top of the inductor, channel B to the bottom, and I'm actually going to take this ground connection out here and pull a resistor in to an arbitrary 22K. Okay, we should now be ready to run the simulation and bring the oscilloscope over. I'll set the oscilloscope up, hopefully we'll get a good wave, and press the button, and I don't get anything too exciting, so I'll have to change a few settings down here, change that to DC instead of AC, and press the button, and there we go, we've got a nice wave. As you can see, we've got a oscillation occurring. I press the button once, and now the oscillation is fading away as that energy diminishes. Unfortunately, it's not a perfect world, and the energy actually diminishes just through the resistance of the wire and is transferred into heat. and by adding a bit more energy we can create the oscillation again. So by creating an additional circuit that actually feeds some voltage back into this circuit, we could continue this oscillation indefinitely. Well, that's just a quick example of a very basic oscillating circuit, and that'll be all for today's video. And actually what we'll do in another video is cover the more complex oscillators